So good morning. We can start the next topics, which is combination of groups and manifolds. We will have now the situation where we at the same time have Lie group and a manifold, and this Lie group is somehow connected with this manifold, that it so-called acts on the manifold. So the crucial concept is action of Lie groups and Lie algebras on manifolds. So this is the primary topic, very important. Actually, the groups are most interesting because they can act somewhere, and the concept of group was sometimes isolated from actions. So what really was present was an action of the group. So some mathematicians distilled this concept to the concept of the group. But now we have to study how the group can be useful, how can they act somewhere. So the action of group is important concept, and it is possible by, first of all, to study actions not of Lie groups, but say discrete groups. It is very important for some parts of mathematics. And then not on manifolds, but on other sets, structure sets perhaps. But our main interest will be in actions of Lie groups on manifolds. So it is a special part of actions of groups on some sets. And for us, it is the most interesting, but the other parts are also interesting, also in physics, by the way. These discrete groups play a prominent role, but now we study Lie groups, and they have Lie algebras. So because Lie groups can act on manifolds, also it concerns somehow what Lie algebras do. So what is the definition? There are two possible actions, as we will see, and one has to distinguish them, but we will see that if we have one of them, we automatically have also the second one. So there are two actions, so-called RG and LG. This is from the word right, and this left. So they are called right actions or left actions, or action from the right and action from the left. And what is it? Both of them are maps. If it is on manifold, M on M. If it is on a set, just M is a set. So for each group element G, we have a mapping which is bijection, bijection of some set. And when we speak of manifolds, it is a diffeomorphism of the manifold written here. This mapping is such that if you study action of element G1, G2 product, then it turns out that there is a composition of these two guys, but in opposite direction. Yes? If here is G1, G2, here is G2, G1. If something like this happens, we speak of right action of, this is right action of G on M. And what about the left action? Similar, for each group element, we have a diffeomorphism in the case of manifolds with the property that if you study this left action with assigned to group element G1, G2, it is then LG1, LG2. So notice that here the order G1, G2 is preserved, here it is reversed. Why we have to distinguish it in several constructions of something in this differential geometry connected with Lie groups. We need sometimes actions of group for some construction, for doing something. And always it is that we need one of them. And you must check that which one is needed and to use this one. And we will see that if you have left action and you need right action, there is a cheap trick to obtain it, the left one from the right and vice versa. So it is important to choose the proper one, but it is not a problem to change it if you have the second one, yes, the opposite. So maybe there is also another way how to write this mapping, the same mapping, that here, in order to obtain the result here, so this is given by M goes to RGM, yes, by definition. RG is from M to M, so M goes to RGM. But you see that in order to obtain this element, we need actually two objects, a point M and a group element. So it can be also written like mapping that give me a pair MG, and I will give you an element RGM in this old notation. So this is just another way how to describe this mapping. It is often used, this way of description, and it has also a small advantage, not in manipulation, I think, but by definition, what is because we have Lie groups and manifolds, so we use manifolds. Yes, also Lie group is a manifold. Here is a manifold by definition. So we have actually two manifolds, and when we map some manifolds, you know that the smooth maps are the most interesting. So also it is important to define what does it mean a smooth action of Lie group or manifold, and smooth action is such that this map is smooth. It is then clear, because we know that this is a product of two manifolds. We know this concept, and we know what is smooth mapping of one manifold to other manifold. So smooth action is such action that this mapping here is smooth, which is something like that. It is at the same time smooth on M and smooth with respect to G, yes, at the same time. Now, when we defined it that it should be a bijection, why? Because from this property, for example, or here from L, from this property, you can easily see that the inverse action or inverse mapping for the mapping LG is LG to minus 1. Yes, if you multiply or compose mapping LG with LG to minus 1, it is by definition G to minus 1, which is unit. And maybe it is more or less clear that R with respect to unit element is identity on M, and also L with respect to unit element is identity. So the action by unit element of the group does nothing. Yes, it is trivial. It is just identity. Perfect. Now some examples. There are many examples, and we will see them. For example, if G is GL and R, and M is Rn. So here we have matrices, here we have columns of real numbers, and they are invertible matrices. So the natural action is that this column goes to this column. So if LA on X by definition will be multiplication of A with X from the left. We can check now that what about LAB? It is the matrix AB multiplied by X by matrix multiplication, but matrix multiplication is associative, so we can write it in this way. This is LB acting on X, and this is then LA acting on LB acting on X. So we see that LAB is LA composed with LB, which is a proof that it is really left action. Yes, this is not right action because this formula came by computation. So whenever you have some suspicion that you have some action, you can check it, whether it is an action, whether it is right action or left action. Something similar like here. For example, so another example, similar, very similar to that one, the same G, GL and R, the same M, Rn, but now I will write directly that it will be a right action that transposed matrix multiplied by X. But this is the small change, that first you produce transposed matrix and only then you multiply this column from the left. Yes. It can be done in principle. You obtain another column from the original column, so perhaps it is okay. Now check what happens on AB. We have AB transposed multiplied by X. But from the properties of transposition of matrices, we know that it is BT80 on X. Here, by definition, it is RA on X. And then it is RB on RA on X. So we see that if we compute the action by product, this is the product, so to speak, of these actions, composition, but in reverse order. So this is a big difference. Yes? Here is real left action, and here we obtain right action. Similarly, you can check that if you put a2 minus 1 here, you will obtain the same result, that because of AB a2 minus 1 is such and such, you will obtain that it is another right action. So you see that at least we have a lesson that whenever you fix a group and a manifold or the set, it is not clear what kind of action you do by these two elements, that the group and M, when are fixed, they can be several possibilities how this group can act on this set, on the same set. And have a look on still other example, maybe even more extreme, that let G be G. It is very deep statement. And let M be G as well. Yes, so G will act on G, on the same G. And how? There are 6 possibilities. 3 of them are left actions, and 3 of them are right actions. So first, left actions. Left action number 1 is multiply G2 from the left. I will check it, that it works. Left action number 2. G1 multiplies G2 from the right, but inverse. And left action number 3, that because of the big success of these two, we can combine them to a single formula. G1, G2, and G1 inverse. So I will check just the first one. Yes, this is called, this particular is called, very important, left translation. It is very important concept of action of group, that group acts on itself by left translation, by this formula. Yes, and is it true that it is left action? That I will check that left translation is left action. So let's apply left translation by G1, G2 on G3. So what is it? It is G1, G2 multiplied by G3, but once again it is associative, so it is G1 multiplied by G2, G3, but this is left translation number 1, left translation with respect to G2 on G3, and then this is left translation with respect to G1 acting on left translation with respect to G2 acting on G3. Yes? So we see that this left translation is really left action. This you should know. What is it? This has also some name, and we already had it. What kind of, or what is the name of this transformation? Do you remember? Conjugation. So we see that conjugation is somehow doing L1 and L2 at the same time. Yes. So L3 is combination of this, and you should check that it works. We already met this. It is I denoted it as IG1 on G2. Yes, conjugation. So conjugation on group now has for us interesting interpretation, that it is some action, very interesting and important action. on the group on itself. Now, we have some mirror images of these three possibilities of left actions to right actions. Right action number 1, right action number 2, and right action number 3. So G1, G1, G1 acting on G2, G2, and G2. Definitions. First, so-called right translation. G2, G1. Right translation. Just multiply the element from the right. In the similar way, like here, you should check that it is really right action. Yes? It is just associative law for multiplication in the group. Here, it is multiplied from the left, but with the inverse element. And here is combined both, so G1 to minus 1, G2 and G1, which is conjugation by inverse element. So conjugation by inverse element is right action. And conjugation by directly this element is left action. Now, why it works, if this works? Because there is a general cheap trick, which is very useful, that imagine that we have some LG, which is, of course, left action from the notation. Then we can introduce some right action by the formula LG to minus 1. Yes. Check this particular R created from left action. How behaves on the product? It is by definition the corresponding left action G1, G2 to minus 1. But G1, G2 to minus 1 is G2 minus 1 and G1 minus 1. And because it is on left action, we have LG2 minus 1, LG1 minus 1. But by definition, this is RG2 and this is RG1. Yes, so we see that if L is left action, then this particular action is actually right action. And the same holds, of course, that you can define LG as RG to minus 1. So this cheap trick you should use whenever you have one type of action and you need the other type for something. So for example, here I defined that LA on X was AX. Yes? It was left action. Now we can define right action, one possible action, as A to minus 1x. Yes. So by this trick, it is clear that it should work, because we proved this trick in general. And also have a look that if those three guys are left actions, that it is clear that those three guys there should be right actions, because just this trick was used. That the essential difference is between left translation and right translation. Multiplication from the right and multiplication from the left are essentially different, but then the other cases are already given by this trick that put g to minus 1 instead of g in those formulas. Yes? And also, maybe it is useful to realize that this action which I mentioned some time ago, that with transpose matrix, it is in indices, it is what? I is transposed I, j, x, j. But transposed ij is aj, I, xj, which is of course xj, aj. These are just numbers. But we see that this is graphically that this x is multiplied from the right by the matrix. Yes. So there is a possibility to write that right action of A on such row x is given by this formula. And the corresponding left action, the first action which was present there, left action of A on such x is a matrix on X. So what is useful to understand that this formula can be also written like that R A on column X is transposed X on the column. It is the same in details. Yes, the formula is like that, which is the same like here. So here you multiply columns by matrices from the left, but not by A, but by transposed A. And here you multiply it by direct A, but from the right. And you obtain in details the same formula. Okay, so we already understand hopefully the definition and some examples that there are examples and maybe quite interesting because of course multiplication of columns by matrices is a very frequent procedure, so it is quite useful to understand that there is some action of some group on these columns and maybe there will be some consequences of this observation. And now we will study some general consequences of actions. There are two important concepts which are present whenever you have some action, that the action combines two things: what group acts and where it acts. Yes? So we have action of G on M. It turns out that whenever you have some action, either left or right, it is not important in this very much. Something interesting happens in G and something interesting happens on M. So both these constituents of this action feel some consequences of the fact that group acts on the set in general. Yes. So what are consequences first on M? That there exists something which is called orbits. That on M, orbits are created naturally by this action. And in a sense, this M decomposes to orbits. What does it mean? What is an orbit? Orbit, here is our manifold M. M, and here is the point M. Orbit of this point is the set of all points M primed from M such that M primed can be written as Rg of M for some G from G. What does it mean? In plain English, that they are all the points on M to which you can go by action of the group, by any element, it doesn't matter. So if you fix this M and you construct all these M primed points with all G elements from the group, you obtain some subset in general. So here is M, and this is OM. So for example, here somewhere is point M primed for some G. Yes, and there is also some M double primed for some other G and so on. So for all G points, you obtain all M primed, and all together they form this subset which is called orbit. Now, there are several basic properties which one should understand when working with orbits. For example, that being or orbit is equivalence relation. On common orbit is equivalence relation. What does it mean? That we can introduce equivalence on M, that M is equivalent to M primed if M primed is Rg of M. That means that they are on a common orbit. And if we have equivalence relation somewhere, it is very easy exercise, extremely easy. So I will not prove it here. The proof is more or less automatic. And it will be given on exercises to prove it. I will show now computations of several orbits to show that how it typically looks and how it is computed. But it means that you can make equivalence classes then on your M when one class is given by one orbit. Another class is another orbit. Also check that orbits cannot be like that. There cannot be intersection of two orbits. That a single element cannot be element of two distinct orbits. Think it over. Yes, why it is so. It is also elementary exercise. So this picture cannot happen. Yes. So there are several lines there intersecting. One are two orbits, and then intersection of as a symbol that it cannot exist. Third property may be that here the orbit was given by this element and all other elements were somehow secondary, but the same orbit can be given by any element from it. Yes. So if M primed are from orbit of M, then this orbit can be described by two ways. That it is either orbit of M or orbit of M prime. It is the same orbit. Because if you can go from M to M primed, you can go also from M prime to M. By which element? If we go from here by element G, say, what G is a group element which puts us from M prime to M? Inverse, yes? So it is clear that whenever you can go from here to here, you can also go backwards. So if the orbit is given like all elements which you can reach from M, then the same elements you can reach from M prime, because at least you can go in the first step back to M and then to all other elements. Yes, so this is important, that the orbit is characterized fully by arbitrary element which is on the orbit. So, yes?
Also work with the left action of G?
Yes, yes. This is definition by right action. By the way, I don't know why I used. There is, of course, there are also orbits. Thank you from the left action. Yes, so I used here right action, but they may be different, of course. Yes, because right action can be different, like left action of the same group on the same manifold. But there are orbits for both of them. So now some examples, because they are frequently quite interesting. Here we have this example, the first one which I used. Yes. So once again, LA on this is AX by left multiplication of matrices. Matrix A left multiplies the column from the left. Now, if this can be understood like action of several groups on Rn, because any group which is given by matrices n by n works in this way. Yes, the biggest one is GL and R, and in the realm of real groups. So let's study it as a GL and R first. It is the biggest one, biggest possible in this situation. And the M is columns, so Rn. Now, let's speculate how orbits are given. What about the orbit of 0? Yes, x equal 0, 0, 0. If we start from 0, when can we switch to which points of Rn from 0 by this action? Only 0, yes? So the full orbit is just one point. So you can see that sometimes orbits are not very big. Sometimes you cannot move from this point by any group element. And what about other elements? So take x non-zero. For example, take 0, 0, 0, 1. It is non-zero column. Yes. Now, if we act by GL and R on this element, we will obtain a column which looks like what? Here you have multiplication that this time this is here. So if here is A11 and A1n, AN1 and ANN, what will be in this column explicitly? Okay, A1n, 2, ANN. So this column, yes, this column of the matrix turns to be the column which is the resulting one. So what we see now, that we can, if we take orbit of this element, we obtain all possibilities of 1n and nn. The last column in the matrix. In the matrix from GL and R. Now the question is whether there are other columns in Rn. This is from Rn. So what is specific for these columns? Are they all possible non-zero columns, or whether they exist elements from Rn which cannot be the last column on GL and R? Yes? This is the question. That we obtain something, and now we speculate whether this something is a general non-zero element or it is restricted somehow. So can it be zero? No. Why? Why here we cannot have 0, 0, 0?
Because it needs to be invertible.
Invertible, determinant, and so on. Yes? So we know that because it came from the last column of the GLNR matrix, it cannot be 0. By the way, when 0 is a separate orbit, it cannot be 0 by definition, more or less. Yes? So this is non-zero element. We start from some very special non-zero element, and we came to a lot of elements. Now the question is that if we reverse it, that let this be any non-zero element. So we put it here. Can we obtain some matrix from GL and R which have prescribed column here, which is non-zero? Yes, the answer is yes, but can you imagine that why? How we should choose other columns if the last is fixed and we want to obtain a matrix from GL and R? What is the condition of the matrix A, which is from GL and R?
They need to be linearly independent.
Yes, so determinant of A should be non-zero. So it is completely enough that these columns are linearly independent mutually and also with this column. So if we fix this matrix, we just need to add other vectors which are linearly independent of the first given vector. And it is known from linear algebra that it is possible, that you can have a part of basis and fill it with other vectors in order to obtain some basis. Yes? So because of this fact, this knowledge from linear algebra, we know that there exists matrix A, which is from GL and R, which sends this vector to arbitrary prescribed non-zero vector. What does it mean? That what is this orbit actually? Yes, the entire Rn with this unique point as an exception. So how many orbits? Each m, whenever you have action of group on orbit on m, your manifold decomposes to orbits. So also this Rn decomposes now to orbits. And how many orbits we computed that they are? Just 2 orbits. Yes, everything without 0 and 0. So you see that there are 2 orbits and they are maximum possible not non-similar one to another. One is extremely small and the other is extremely big. So we see that to study the structure of orbits can be sometimes quite interesting and quite surprising, that what is the structure of orbits of this action. Now, let's restrict the study. Let's take the same orbit, the same action, but study the matrices which are not from GL and R, but only from SON. So it is restriction of this action to subgroup SON. The same formula. So LAX is AX. Now, what about orbits? We can use these facts, which we already know from this computation, that if you start from x equals 0, goes to x equals 0, yes? So we have an orbit, the origin of Rn, as a single orbit, or an orbit with a single point. Now, what is the orbit of once again this 0, 0, 0, 1? It is again this A1A, 1N, and NN. But now it is again this column, but now this is a column not of a GLNR matrix, but SON matrix. And SON matrix fulfills this property. This is the definition, and determinant. A is +1. And this can be, if you do it in indices. So do you know what these conditions say in indices for the matrices? In indices means that for columns and rows of this matrix, that what property of columns and rows of matrix A are written in these equations. Do you know it from linear algebra? Perhaps I am sure that it was mentioned there.
It should be orthonormal.
Yes, that both rows and columns are orthonormal system. It is this and this. And what then adds this fact? That there is some orientation. Yes? So it is something like right orthonormal system. So what we know already from here, that this vector is not arbitrary, because now it is a column of special matrix, of SON matrix, and because all columns of SON matrix produce an orthonormal basis, so this vector should have length 1. Yes? So this vector should have length 1. So what does it mean? That from this vector, which clearly has length 1, we go to arbitrary vector this with the only restriction that it has length 1. Now, what are the vectors symbolically? I just draw 3 axes, but imagine an axis. So we start on the last coordinate, which is here x3, 1, and all other zeros. So it is somewhere there in Rn. And now we go somewhere to other points by this action, by general SON matrix. And what is the resulting set? What compose all vectors normed to unity? A sphere, yes. So this is from the sphere in n-dimensional space, n-1, and with unit radius, yes? And what about the change to some, not 1, but other positive number, if we have some small r? Yes? Na zdrowie. So if we have not 1, it will be, here is 1, and here is somewhere some r.
It's a -1 sphere with the radius r.
Yes. So if here is r, here will be r. Now, the opposite question. We are somewhere on this sphere. Yes? So we are somewhere, it means that we are a column which has the square r squared, or the length r. Yes, we are on the sphere. Somewhere here, or here, general point. So the only restriction to this position is that sum of squares of these elements is r squared. This is the definition of the sphere. Yes, so we have elements with the restricted sum of squares, and we put it here. So now is it possible to find well, here is r. So now this has square of squares. The sum of squares, you have r squared. So what matrix should do it? Orthogonal matrix. And the question is whether there is an orthogonal matrix which sends this element to general set of numbers here, with the only restriction that sum of squares is equal to r squared. Yes. Once again, think here should be fixed column, and the rest should be orthonormal. Yes, orthonormal basis. So, is it possible to, if you have one normalized vector, is it possible to add other normalized vectors such that they form orthonormal basis? Yes, by some theorem of linear algebra. And even such that it is right-oriented. By the way, this orientation is something which is studied properly next year in mathematical physics number 2. That maybe I speak in some loose way now about it, but it is quite simple and precise thing. What is it? So you will see in a year. So what are now orbits of this action? We have action now of where? Of GSON. We discovered that the whole space Rn decomposes to two spheres with the center in the origin of all possible radius. It is something like onion. Yes, the infinite onion becomes this Rn. And we see that here the structure of this orbit is also interesting, that all orbits are similar one to another. They are spheres, but just bigger, except for the orbit in the center, which is not very similar to sphere. It is sphere of 0 radius, but here are n-1 dimensional manifolds, all of them, and the origin is 0-dimensional manifold. So in general, orbits can have various dimensions. Here we see quite simple situation, or we saw for GL and R that one orbit was n-dimensional and one orbit was 0-dimensional. It is very big difference. Here, one orbit is 0-dimensional and all other orbits, which are infinite number of other orbits now, not just two. But one orbit is still 0-dimensional and all other orbits are n-1 dimensional, and they are very similar. They just differ by the radius of this sphere. Maybe we also will have some knowledge of some other orbits, but now we go perhaps to the other concept. So we first studied what happens on M because of the action, and the answer is that M is decomposed to orbits. This is a novel property of M, which was not present before a group acted there. It is a consequence of the action of the group. And something also happens in the group in general. So we have G and M. Here are orbits. And here is something which is called stabilizer. So what is it? Once again, here is M, say with left action of some group. And we will have some point. So this point creates orbit, we already know it, but it also creates something in the group, namely the stabilizer. And what is it? It is called GM. It is stabilizer of M. It is the set of all group elements H such that LH acting on M is M itself. So they do not move this M away. They left it alone as it was. We will see also examples on it. Now I realize that maybe I will use sometimes some short notation. So short notation, LG on M, or is the same thing like GM, and RG on M is the same thing like MG. It is often used, this notation. Yes, so just write the element of group left to the element on which it acts. It is a little bit shorter, as we see. And the property that LG is left action, here is the property that G1, G2 acting on M is G1 acting on G2M. And here the property that here is, check this property, that we know how this property looks in the old notation, and check that in the new notation it looks like that. And this right action is that M on acting of G1, G2 on M is MG1 and G2. So this written in the old language inverses the order. So but very important thing is that this is no multiplication, that sometimes you have not possibility of multiply element of G with elements of M. In some actions we already use that. For example, in this, you can multiply this element by matrix multiplication. So if I write AX, I can think of two things, either abstract left action in this notation or matrix multiplication. So in this is an example where two interpretations are possible of the same writing, but in general, here it shouldn't be interpreted that there is some multiplication. It is just a shorthand notation, nothing more. And the other counter example to the statement that sometimes it is multiplication, if it is left translation on the group, it was given by multiplication. Yes, that left translation on G, the formula is GH is GH, and now it can either mean that it is just abstract left action, or it is multiplication, because G and H are elements of the group, and the multiplication is possible there. Yes. So here, what is meant is multiplication in group. Yes, it is the left action is given by multiplication in the group. It is not just a shortened notation. So let's go back to this fact. Now I will use the old notation that the statement is important, that this set, it is until now it is a set. All group elements with the property that when you act by these group elements or on your fixed M, from M, it doesn't move. Now, let us check that these H's or all possible element group H with this property form a subgroup, that they are closed with respect to multiplication. Of course, unit element is here because L with unit element is always unit map. So for unit element it is closed. It is true. And now if we have two elements and they act on M, we know that it is LH1, LH2 on M, but now we suppose that LH2 on M is M itself, because it is from GM. This is assumption. And LH is also from GM, so it is M once again. So we see that also the product of these two elements from GM is also from GM, because also it also left M untouched. So we just found that GM is a subgroup of G. Not just a subset. Now, it is quite important to know that what happens if you find these stabilizers for two elements on the same orbit. So this is OM, and the same like OM primed. And stabilizer exists for any point on your M. So in particular, it exists here, and it exists here. So GM, there is GM and GM primed, and they are two subgroups. In general, it can be easily shown that they are isomorphic first, and even we know the isomorphism, that isomorphism is conjugation. So what happens? We can go from here to this point M prime by some group element, by some, say H or G. By definition, because we are on the same orbit, there should exist G such that acting by G on M, you go to M primed. Yes, so M primed is GM in this new notation. LGM. Now imagine that we have some H which is from stabilizer of M. That means that LH acting on M is M. And by definition, H primed is from GM primed if LH primed on M primed is M primed. So we suppose that we know this subgroup, this stabilizer for some M, and now here is a definition that H primes which are from GM primed have this property. And now this is a question that how are these two elements related? And it turns out that H primed is conjugation by G or G minus 1, I think the G, of H. This is the statement. I will have a look. Maybe I should know it by heart, but it looks like that. We can check it, yes? That, what about this action of H primed on M primed? So, if it is true that it is conjugation, it can be, by the way, computed. I just wrote the result and check it, but it can be nicely computed. So it is left action by conjugated H, that is G, H, G to minus 1, acting on LGM. Now, this is, because it is left action, it is LG, LH, LG to minus 1, and it acts on LGM. So here, you notice that these two guys, LG to minus 1 and LG cancel. So it is altogether LG, LH acting on M. But LH acting on M is M, because H is from stabilizer of M. So we obtain LGM, but it is M primed. Yes, so in some reverse way, you can discover that what is the relation between H and M primed. I knew the result, so I did just the proof from the known result. So what does it mean? That it is true for any element, so it can be written like that: GM primed is IG of GM. What does it mean? That when you take all elements of GM and make conjugation of all of them, you obtain some set first, and this set is, you can check, it is directly the stabilizer of this M primed. So this is this property written all together for the whole subgroup. Yes, so there are two subgroups. Here you have GM primed. For this point you have subgroup GM. They are both, GM is subgroup of G and GM primed is subgroup of G, two subgroups. And they are related by, in a simple way, by conjugation. What is the picture for it? That here is our G. Here is somewhere unit element in this G. And we have some subset, GM. It is a subgroup, we checked it. So it should contain unit element. Each subgroup contains unit element. So GM looks something like this. Yes? Now, what about the picture of GM primed? It should be schematically, of course, something like this. Another subgroup which also contains E. And what is important now, that this formula, you see that here is IG. IG is left action, we already know, the conjugation is left action, so it can be re-inverted. And if we apply, so to speak, IG2 minus 1, we see that I conjugation with respect to G2 minus 1 to GM primed is GM, which means all of that you have actually a bijection. Check and think that this says, all those formulas, that we have a bijection between these two sets by the conjugation. A bijection is given. And we already know from conjugation that it is a homomorphism. Yes, that what it means that IG on H1, H2 is IG on H1 multiplied by IG of H2. That conjugation is homomorphism. And it is also a conjugation of subgroup. It is also a bijection. So it is homomorphism. Bijection, it means that it is isomorphism. It is homomorphism, but plus bijection. So it is an isomorphism. GM to GM primed in this case. So these two subgroups, one of them is stabilizer of some point, the other one is stabilizer of another point on the same orbit, which the points are related by group element G. Then their subgroups are also related, and they are related by conjugation. So the subgroup of M primed is conjugated subgroup of M. And conjugation is isomorphism. So that means that if you compute stabilizer of this point and this point, you obtain isomorphic groups. And we know also already this isomorphism even, that the isomorphism being conjugation. So if you just want abstractly know that what is the stabilizer, it doesn't matter which point you check for the finding of stabilizer. Because if you choose other point of the orbit, you will obtain isomorphic group. The question?
Is it important that the stabilizer was defined with the right action?
If you know, you can do all that for right action. You also obtain stabilizer, which can be different, of course, because the action is different. And maybe the conjugation will be with G minus 1, I don't remember. You should check. You also obtain the same phenomenon that if you are on the same orbit, the stabilizer of right action are isomorphic of these 2 points, with isomorphism being conjugation, but I don't remember by which element. You should check. Yes? And there is just some byproduct of this thinking, that notice that we have a new action now, which will be quite interesting in some time. Now we have action of the group on subgroups of this group. So if this is any subgroup of our group G, let's call it some H or something like that. So let this be H subgroup of G. Yes? Then you can act on this subgroup by conjugation. You obtain another subgroup, which is isomorphic to the original one, and think it over that this is action of G on subgroups of G. It is left action. You should check it. Left action of G on the set of subgroups of G. So you think of all possible subgroups of G. And then the conjugation can be regarded as left action on this set. There are also orbits, as always. Yes, you have an orbit that one fixed subgroup and the orbit given by conjugation of these subgroups. They are isomorphic. Check, yes, that the conjugation somehow connects those particular isomorphic subgroups which are given just by conjugation. And now we can try to find some interesting stabilizers. So we want to compute some stabilizer for some particular actions. For example, this action which we studied already, that G is SON and N is Rn, given by, say, left action on X is AX. Yes, so graphically but not GLNR, but SON. So we can compute stabilizer, for example, of the north pole of some sphere. So this is a north pole of, it is of course north pole of Sn-1 with unit radius. Now we want to find stabilizer. So what particular matrices form this subgroup which is stabilizer of this particular element? Yes. So it is, here you have the sphere, here is point N in many axes. And you can apply SON on it. What does it mean? That you rotate the points of your Rn. Rotation about this center. Yes. Now the question is, what rotations preserve this north pole? Do not change it. So once again, we know, we already computed it, that here what we obtain is this column. Yes, so it is A1, N, N, N. But now we do not compute orbits, but we compute stabilizer. So it should be the original vector of, or point of North Pole. So this column in this orthonormal matrix, orthogonal matrix with determinant 1, sorry, should be 0, 0, 0, 1. It should be, this column should be as the last column of the matrix from this computation. So our matrix looks necessarily in this way, that here is 0, 0, 0, 1. Otherwise, it moves this North Pole to some other point of the sphere, and we do not want it. Yes, now. So they are still remaining n-1 columns, and we don't know what is their structure. Are they arbitrary or what? So remember that the fact that this is from SON, this matrix should be from SON, means that all columns and all rows are orthonormal. So now the question is, what is the last row of this matrix if this row should be normalized to unity?
The same zeros.
Yes, there is no other possibility like zeros, because also already this number 0 gives you the length unity. So here should add something to 1, and we do not want it. And here is some b. But this b is already n minus n times n minus n dimension. Yes, one dimension less. So this a looks like b0, 0, 1 if it is to preserve this North Pole. But now this a has to fulfill this property. So what is AT if A is like that? It is BT0, 0, 1. We see it. So now if you multiply those two guys, you will obtain, for example, in this order, AAT, it will be BBT 0, 0, and 1. But it should be unit matrix, so 1, 0, 0, 1. So what we see that BBT is 0, not 0, sorry, unit matrix, but n minus 1 dimension unit matrix. Yes, here is dimension n. So we are, but what does it mean that B is from ON? If A is from SON, it necessarily has such structure, this subgroup, with B from ON. But there is also the condition on the determinant. What is determinant of A, which has this structure? Because it is block diagonal, it is determinant of B multiplied by determinant of 1 of this matrix, which is clearly 1. So it is determinant of B, and it should be 1, determinant of A, yes? So determinant of B is also 1, so it is not from N, but this and this is that B is from SON minus, sorry, it was not ON, but N minus 1, yes? 1 dimension less, N minus 1. So this is the end of the story. Now the So G for North Pole, sorry, 0, 0, 0, it is the stabilizer of the North Pole, is given by A, which has the structure B0, 0, 1, with B from SON minus 1. And of course, this is from SON. So the stabilizer is given by special set of matrices, which are block diagonal with SON element on the left upper element in the block matrix, and 2 zeros and number 1 added. So we can check whether it is a group. So A1, A2 of this type is B1001, B2001 block diagonal, which by multiplication of block diagonal matrices is B1, B2, 0, 0, 1. And we see that if we have a mapping that B001 mapped to just B, and this is from SON minus 1, and this is from SON, we see that this gives you an homomorphism of this product. So our final result is that the stabilizer of the North Pole of this point, 0001, is a subgroup of SON, which looks like that. And because of this relation, it is isomorphic to SON minus 1. So the stabilizer of in SON of the North Pole is a subgroup which is isomorphic to SON minus 1. Let's do it just for n equal 3 in standard, in this really this picture. Yes, what does it mean? That they are SO3 are all possible rotations around the origin, and now there is some SO2 subgroup or subgroup isomorphic to SO2. What are SO2? They are 2 by 2 matrices that rotations in a plane around origin. Now, what are these rotations? They are rotations around this axis, nothing more. Because what rotation can you apply in order not to move the North Pole? Just rotation about the axis on which it sits. Yes? So the result is clear from SO3, but it is now computed for SON in general, North Pole, something like North Pole, and we see that it can be nicely computed and the result is understandable. So, thank you.